Hello, CCP1 students. This is Dr. Kirschner. This is a lecture for Thursday, January 28th, I believe it is. This is the first lecture of Chapter 7, and I'll be back next week to continue on with Chapter 7 and stuff. So I hope you guys are doing well. So anyway, let me get to the lecture. A lot of this today is non-mathematical, not very conceptual, but almost a history lesson. But it also serves to make sure you know different names for different groups and different nomenclatures for looking at the periodic table and being able to sort that all out. So you'll see that as I go through some of the homework, some of the things that are kind of detailed information that you need to make sure you have a good handle on. We kind of inherited with the periodic table some old group nomenclature that we're going through, and there's also some names that people use to refer to different groups that we have to get a good handle on. So that's what mainly this lecture is about. The lectures after this, when you come back, will be about when we know the position of an element in the periodic table, instead of just saying what group it's in, we're going to talk about whether it's going to lose electrons, gain electrons, ionic bond, covalent bond, and do all sorts of stuff. And that will be the biggest meat of the material. And that can be kind of tricky, but today's lecture is mainly kind of like, where did the periodic table come from? All right, whoops. Let me get rid of this screen here and get to the right thing. All right, so here we are. So we're doing sections 7.1 and 7.2 today. All right. Well, development of the periodic table. It says electron configuration in the periodic table. The standard long form of the periodic table is so constructed that the position or location of that particular cell, that square that has that element, the element of the table, gives a great deal of information other than, oh, it's a halogen or whatever. It actually will tell you by left or right whether it's going to gain or lose electrons or whether it's going to share. It will even tell you whether it's acidic or basic. It will tell you how fat it is as far as how the number of shells around it and stuff like that. Anyway, as each element is unique, so each cell location of the table gives us unique data. Rows and columns have specific trends. Again, we start that next time. Students are challenged to understand these trends, which are often based upon our electron configurations. So let's go there. So let's go back to history first. In 1929, the German chemist Johann Wolfgang Dobenreiner proposed that there were triads of similar elements related by their atomic weights. He was able to produce a more complete table because he wasn't able to produce one, because many of the elements had yet to be discovered. So let me explain what that means. Okay, so in the history, way back when, they had about, you don't have to know the number, but 40 to 50 elements discovered. Now, to make a periodic table today, we have 92 elements that are natural, and we have 118 total when we put in the heavier ones above uranium that we've synthesized, even though a lot of them don't survive more than a couple seconds or a couple minutes or whatever. So anyway, to make a pattern or to make a table that put them all in the right location is really hard when you have more than half of them missing. Anyway, what was important about this is there were two camps of people who were organizing elements. Believe it or not, number one, I want you to assume that people way back then could actually tell that they had a pure substance. Most things you deal with on this earth that you have samples of are by no means pure substances. Even the purest water is not a pure substance. There's always stuff mixed in. Number two, that when they had a pure substance, remember it could be a compound where you have atoms bonded together that are not the same elements, that they actually knew they had an element. And they knew that because it couldn't be broken down into smaller compounds. And then finally, number three, big number three is this. They were starting to get atomic weights of the elements. That's a long story, but they were starting to do that, and it has to do with the fact that if you put elements into their gaseous state, they take up equal volumes of gases of elements in their elemental state, take up equal volumes. So if you weigh equal volumes of gases that are at the same temperature and pressure, you can compare weights and know that you're weighing the same number of elements. So anyway, so this guy, what's so unique about him is that on the one hand, there were chemists who were saying, I noticed that some elements are like each other, which by the way is our columns in the periodic table, common properties. But at the same time, if you go across a row, that our elements, both atomic weight and atomic numbers, are going up. This guy actually was able to see with very few elements that maybe both trends were right. It wasn't until much later with Mendeleev that this was proven correct. So I want you to put Dobenreiner as someone in your homework. So keep that filed away. Dobenreiner was someone who was able to find triads and stuff like that. So here are some of the triads he found. So lithium, sodium, and potassium. Not related at all by weight because there's a lot of elements between lithium and sodium, for example. So to say, well, lithium and sodium are very common chemically, he had to propose that you have to kind of like rewind this table. He didn't make a table though. This is showing the real periodic table or part of it and why they're related, but he picked out these triads here. But he had no idea why they worked that way. He didn't really understand how many elements were in the middle or that this was going to be a grand table, so to speak. Okay, so why did the periodic table have to develop over time? You don't have to memorize this by any stretch, but again, there was very few elements that were known when he did this. So a lot of the elements were discovered later, so it just shows you how many elements were missing. Then, next guy to put in your homework is called Newlands. So this time he did do, just like Dobenreiner, he came up with the fact that you could organize elements not just by atomic weight, but also by common chemical properties. You could do both. Again, that's what the other guy did, but he didn't understand how to do it by both. What he came up with is a musical scale. In music, you go C, D, E, F, G, A, B, C. In music, you have 7 letters or 7 musical notes. Every time you go through the 7 to the 8th one, you actually get the same note again, and it ends up being twice the frequency. Anyway, this is his analogy. If you take hydrogen and you want to find another gas or another element that's like it, if you order them by increasing atomic mass and you go every 8th element, you're going to get someone who has the same characteristics as the element 7 ago. Here's another 7 elements, you get another one that's just like it. Gas, gas, gas. They're all gases. So he noticed that if you arrange them by atomic weights, and you could get these things called octaves. So anyway, here's this Newlands octaves. It turns out the scientific community totally rejected him as far as this and thought there was no reason or rhyme or reason for any of this. So anyway, so he was almost there with the periodic table. Then Cannizzaro was a big breakthrough. Now, this is kind of a small breakthrough, but it's still there. The people before him, Newlands and the other people, were kind of lacking one thing, and that was their atomic masses weren't quite right. They were and they weren't. So what I just showed you was right, but there's a lot of other ones that were wrong. And so if you're going to arrange your elements by increasing atomic mass, which will give you going across the row correctly, you're going to have a lot of things out of whack if you're not doing it accurately. So despite the fact that Dobenreiner and Newlands could find these, and even Newlands was actually putting them in the right order, some of the other ones were not falling in the right order to see more trends just like this. So anyway, what happened was Cannizzaro figured out what I just said before, and that is, if you take the masses of equal volumes of gases, but not solids or liquids, you'll end up getting the right atomic masses. And he convinced the chemical society of the world that that's the only way to do it. So the breakthrough here was the fact they were getting the right atomic masses and accurate ones. So they were actually they now could put the elements in the correct order. And if they can put them in the correct order by atomic mass, maybe they can see the repeat pattern we've been talking about a little bit more clearer. So put Cannizzaro as another name in your hat as far as who did what, to when, to how, or whatever. So anyway, Meyer then came along. He's a German. He described 28 elements, and he did by both properties and atomic mass, just like Newlands and Dobenreiner. But he did it to a lot more, and now he had the right masses and stuff. And he started to make a table, actually. Only problem with this table, why don't they call it the Meyer periodic table? Because he proposed that they knew all the elements, and he didn't, wherever his method didn't work, he didn't fudge the data. He just made it work when it didn't work. Whereas when we go to Mendeleev, the Russian guy, he actually left gaps for undiscovered elements. He didn't force his data to work. He just said, well, the reason I don't have one in this category is because I don't have that element yet. And he was right. There's a lot of undiscovered elements. In fact, during his lifetime, those little missing cells, like here, and a few other places, were discovered. It turned out a lot of the elements they hadn't discovered were more rare. They're also very closely aligned to the properties of ones they already had. And it was the Bunsen burner and the spectra, the photoelectric effect, that allowed them to figure out whether some new material was new elements. And some of the elements they found, they got the atomic mass and they found some of these gaps. And sure enough, he actually predicted their physical properties, even their densities. So the gaps is what makes Mendeleev's table better than Doppenreiner's and gives him the credit, whereas Meyer's kind of like a afterthought in the literature. So now we got a modern periodic table. So our next job is to kind of describe how to look at things and how to name things. What's a row? What's a column? How come there's a couple different ways to number the columns across and all this other stuff? What do we call this section of the periodic table? What do we call this? So kind of keep those in mind. But for now, what you've had is a brief history lesson and some names to know for future quizzes and also for future tests. We do want to know these things for this, where these things came from. Okay, so what comes after this? So as it says here, he predicted some of the gaps, and they were found during his lifetimes, and many others were found after his lifetime. Now, it turns out, so Mendeleev, as it says in one of the questions, he organized the elements, and Meyer for that matter too, by increasing atomic mass and by common properties by columns. But look at the periodic table above you in the class. And the masses, of course, are below the element symbol and their decimals, but the atomic numbers are up in the upper right in blue. If you look at it closely, the elements are actually arranged by both increasing atomic mass and increasing atomic number. They didn't know what the heck an atomic number was back in Mendeleev's day. Remember, Thomson had not found the electron until a couple decades later. Rutherford hadn't found the nucleus until even later than that. So they didn't know what a proton was. So anyway, it turns out if you look closer, there's two places in the periodic table where the two elements do increase by atomic number, proton number, but they actually go down in mass. So in some ways, Mendeleev was off by in two places because he did it by mass, not atomic number. So what happened was Moseley found a new technique. It's called it uses X-ray radiation, and he found out that when he put different elements in there, he got certain results we don't want to get into. But anyway, each element gives a different pattern. From that pattern, you can actually figure out how many protons it has. So anyway, what he found was that every element has a unique whole number, not decimal, number of protons. And so if you're asking, are there any other elements to be discovered, you would look through the numbers of protons and say, well, there's no gaps between 1 and 92, and so there's no elements unless there's ones above 92. Well, we made 93 through 118. And they haven't been found in the universe. A lot of them are very unstable, they're radioactive, and they don't survive very long. So indeed, we have found all the elements. So now, the modern periodic table then, technically, is not by atomic mass and common properties, it's atomic number and common properties. So make sure you make a note of that for your homework. A couple things about the modern periodic table. Okay, so first of all, nomenclature of the groups. So by the way, these guys down here, 1, 2, 3, 4, 5, 6, 7, you might say are the rows. Please put down that rows are periods. What is a period? It means as you go across a row, you get a predictable change or trend of different properties. So you start out with soft metals. If you have a D block, you end up in hard metals. You become a metalloid, a nonmetal, a halogen, a noble gas. That's called a period, a cycle of events that's totally predictable. So they call the rows periods. Now notice the periods or the rows have different numbers in them. So it turns out the first row is only 2 elements. There is no metals. Second row has no metals, but has more of a p block. It has a p block. Row 3 is the same as row 2, but row 4 has metals. By the way, if you remember from the electron configurations, row 6 has an F block that inserts. So can you imagine how hard this was to actually organize this and make it all fit when you have rows that are totally different lengths than each other? So if you actually made this periodic table to fit all the real columns, you would have to increase this by 14 since 14 elements insert between the S and the D. So anyway, a couple of the nomenclatures though. The main group elements under the old nomenclature of what we put for the column numbers was called 1A, 2A, and then 3A, 4A, 5A, 6A, 7A, and 8A. Notice that we're only counting the S block. We're ignoring the D block, and then we're putting in the P block. I'm going to tell you later that one reason to do that is that a lot of the more interesting chemistry occurs between elements in the S block and the P block, the ones we do the most reactions with. It's not to say metals don't do interesting stuff, but anyway, the other reason is what we call valence electrons. So another question on your homework. You only count the outer shell. Valence electrons are outer shell electrons. But you only count the S electrons, so you'd have 1s here, 2s here. You do not count the D electrons, even if they're there. And then you count the P electrons. So this would be P1, P2, P3, P4, P5, P6. If you add the S and P electrons together as you go across the row, you get 1, 2, 3, 4, 5, 6, 7, 8. And we'll be talking about the octet row as we bond atoms together. They use their S and P outer shell electrons to get to 8 most of the time at least. But these guys, these D shell electrons, are not normally involved in bonding, so we ignore them. So that's one reason to go 1, 2, 3, 4, 5, 6, 7, 8. It's a way for people to say, I know how many valence electrons this atom has. I know it by the group number. We now go by the new nomenclature. We go 1, 2, we count the middle part, 3 through 12, and this is what's on the periodic table above you, above the board in class. These elements are called the outer transition elements, and we'll get to that in just a minute though. So valence electrons are the outermost electrons in bonding, and they're in the main group, as we just said. Let me see if I can move this for you. Sorry about that. And they're given the A group number, so that's what that is. Okay, let me go back to here. The 4 blocks of the periodic table represent the electron energy sublevel into which the last electron resides. I think we've stressed that a lot, but we'll do a couple things real quick. The B elements are called outer transition elements because they fill the D orbitals, which are closer to the nucleus than the outer valence electrons. Do you remember that 3D was closer to the nucleus than 4s? Think about that again. Remember 3D was filled before 4s? That's what they're saying here. That just explains why they call it outer transition. So just remember that the D block is called the outer transition elements. Just another vocabulary term. But now, the last 2 rows, which are taken out of the periodic table, but they insert into the 6th and 7th, they're called the inner transition, as they place electrons into F orbitals, 2 energies below the valence electrons, which are the S and P electrons again. So anyway, just remember outer is your D block, inner is your F block. So anyway, here's some of those elements. Now what I'm trying to say about the electron configurations. Let's look at it. Everybody, and this will be some questions on your homework too. Can you find the element with this outer electron configuration? I'll say S2, and you'll say it's anybody in this group. Everybody in this column is S2. Everybody in column 1 is S1. Everybody in this column is D1, D2, D3. I'll explain this some other time why these are D5s, both of them, but D6, D7, D8, and why both of these are D10 later on. Then P1 for this column, P2, P3, P4. This is called the distinguishing electron. So there's several homework problems in which I say which element would have this distinguishing electron. So let's say 4P5. Okay, P5 is here then. P1, 2, 3, 4, 5. Did I say 4 or 5P? I think I said 5P. So we have to go to the 5th row. 2, 3, 4, 5. Bingo! Don't have to look it up though because you guys are pros at this from doing electron configurations. If I said 4D2, D2 is here, and I have to go to the 5th row for it. There it is. So those are some of the problems you'll get. So anyway, we use the 1 through 18. That's the more modern one. But if you can know at least where the A versus the B's are, the B's are actually in the inner. We don't give column numbers for the F block though. All right. Why are there two different sets of numbers? B elements are chemically different because of their D cell electrons being filled. They do what are called metallic bonding later. A elements have totally full or empty D shells. So anyway, so we use the 1 through 18. Okay. Representing free elements in the chemical equations. Here's some other things here that we're going to go to. And actually we're done. But let me go back and let's go to your homework and look at some of the problems and make sure we covered everything. Then I give a full shake to everything. So here we go. Original periodic table arranged them horizontally. That means going across by their increasing atomic mass. Vertically by their common chemical properties. Was the first scientist to look at triads. You can look that up. Increasing, who was the first scientist that recognized periodicity of elements when they were arranged by increasing atomic mass? That was Newlands. What did Moseley discover? How does this change? Was it horizontal or vertically? Obviously it was horizontally because it's now an atomic number going across. Then you can say, well, you can combine nomenclatures and say, okay, if I look at 7A, what column through 1 through 18 is that? Since that's the main group elements, that's actually column 17. Which is group 3B? What is group 3B? You'd probably say a metal. 5B, a metal. 5A, that's actually group 15. So what I'm trying to do for number 6 here is, can you give me a group number for these guys? So converting from one nomenclature to the other is not as hard as it looks. Okay, which groups are the main groups? It's 1 to 2 and 13 through 18. You can see that though. Are most metals considered main group? Nope, they're actually the outer transition. Well, they're two different names. They're called the inner transition, but they're also called, I forgot to say this, the lactonide and actinide series. Which ones are considered valence? S and P's. What is the valence number? Notice these are all A's. You just look at their group number. 1, 5, 8, 2. But now if we go to group 14, here's the trend. So what group, by the old nomenclature, is group 14? You'll see that if you look it up, it'll be 4A. Just remember to subtract 10 from the group number if it's 13 and above. You'll get the A number and you'll get your valence. So this is a valence of 4 because it's 4A. This would be group 3A. This would be 7A. Here are some names: alkali metals, halogens, chalcogens, metals, you can call them that, whatever. Noble gases. Then you can look at this. S1 would be your alkali metals. This one would be S2P5 would be halogens, alkali earth metals, metals. And then if you want to do elements by their common properties, they have to be in the same column and have the last shell exactly the same, like P5 or P4. So we look for another P5. There you go. S2, look for another S2. And then there's two that actually do not fit together at all. One is a P6, which is a noble gas, by the way, and this one is by itself. So anyway, that gives you some of the weird questions with this. Mostly conceptual, no math, nothing, just kind of a mess of terms and ideas and some history behind the periodic table. Otherwise, that's it. So I hope you guys have a great week. Hopefully you had a good test and everything, and I will see you next week.